If you've ever heard that nature emits way more CO2 than humans do, or that one volcano emits as much CO2 as all of humanity ever has, or the rise in CO2 cannot be due to fossil fuels because trust me, bro, this video is going to show you just how bad those arguments are because of how ridiculously well proven it is that the rise in CO2 that we are seeing is absolutely due almost entirely to fossil fuel combustion. Even if you have looked at this topic before, I promise you are going to look at lines of evidence that you have not seen before. We're actually going to look at 8 different independent lines of evidence that all prove that this rise is due to fossil fuels. 8 different layers of observational evidence. We are not looking at climate models. We are not appealing to consensus. We are going to look at the actual real world data to understand why this is so widely agreed. And I really think that you will conclude that it is the most logical explanation after looking at this video. But before talking about the cause of the rise, let's establish the rise itself. CO2 concentrations have risen from around 280 parts per million in the pre-industrial era to 427 parts per million at the time of recording this, rising every year by about 2 to 3 parts per million per year, every single year. And we know this really, really well. The most famous record of CO2 concentration is without a doubt those from the Mauna Loa Observatory in Hawaii, famous for good reason because it was the first CO2 measurement record and is therefore the longest running continuous record. This CO2 record was started by Dr. Charles David Keeling in 1958, and the resulting graph is therefore often referred to as the Keeling curve. The sawtooth pattern, by the way, is simply the result of seasons, winter-summer cycle, plants taking in and releasing CO2, and it tracks the northern hemisphere seasons because that's most of the Earth's land. Now, you will sometimes hear people criticize the fact that Mauna Loa is a volcano, but of course, Mauna Loa is famous only for being the oldest continuous record. It is not the only record. We can add to this chart, for example, another long-running record at Nuat Ridge in Colorado. You can see it agrees very well with Mauna Loa record. Also Barrow, Alaska and Key Biscayne, Florida. Again, 2 long-running stations that agree very well with the Mauna Loa record. And here are 74 more. Yeah. You can see the different points on Earth that are represented. Again, this is real data. This is my own work. I downloaded all of these data sets that you're going to see, put them together in Python, and displayed them here. So this is real data, all aggregated together into a single plot. So because we're going to look at other organizations, we can take the mean of the NOAA stations and show them here. And next we will add the ICOS network in Europe. So you see the big cluster of dots in Europe there. There's 95 stations that we've just added to our plot. Again, we'll take the mean of that and add in Deutsche Wetterdienst, the German weather service, and 15 stations managed by CICERO, the National Science Agency of Australia. Environment and Climate Change Canada, 16 more station records there. Sprinkle in a few from the Japan Meteorological Agency. Laboratory for Climate Environmental Sciences of France, throw them onto the pile as well. The Korea Meteorological Administration, more the merrier. And here's data from 51 other national and international organizations. 51. These are compiled by the World Data Center for Greenhouse Gases, a program to collect and maintain this data from around the world. This organization is managed by the Japan Meteorological Agency. And all of these, by the way, are just ground stations. We can add to these measurements from different sampling techniques. For example, NOAA has a big network of radio towers to get CO2 at different atmospheric levels. They also use planes. You can see one of their planes here with a little sampling device on it. They use ships crossing the ocean and balloon-based measurements called air core. And all of these measurements are further validated by satellites, such as NASA's OCO2 and Japan's GOSAT satellite that precisely measure atmospheric concentrations in perfect agreement with what we get with all these other methods. In total, more than 60 different organizations, all working independently with different techniques from different places on the planet, all consistently getting the same numbers every year. Like if 5,000 people from around the world, most of whom never even met each other, all weigh a thing and they all get 1 kilogram as their number, most reasonable people would probably conclude, yes, that item actually weighs 1 kilogram. But yes, if you want, you could try to claim that all of these different organizations are fabricating data and have been for decades. Thousands of people voluntarily agreeing to throw away what may have otherwise been meaningful careers for a life of simply making up fake data, without a single one ever coming forth to whistleblow or provide a shred of evidence that this incredibly well-coordinated scam actually exists. If you actually find that a better explanation, fine. What can I do? But at least try to understand why some of us find it simpler to just conclude that they all measure the same number because that's the actual number in this actual single atmosphere that we all live in. Oh, and by the way, it is worth mentioning that if you wanted to, you could get a CO2 measuring device and go outside and prove it wrong tomorrow. There are dozens of commercial CO2 measuring devices for purposes like greenhouses or HVAC systems or food safety or beer brewing, like measuring CO2 for purposes totally unrelated to climate. You could buy a device like that for like $200. Go outside, disprove these numbers in 1 second. It's your money, knock yourself out. Now, of course, there are those who found this up to now to be pretty boring because all I've shown is that CO2 is rising, not that the rise is due to fossil fuel combustion. But of course, I have not even started talking about the 8 points that I mentioned at the beginning yet. 8 different lines of observational evidence that prove that this rise is absolutely due almost entirely to wide-scale combustion of fossil fuels, which power a growing civilization. So the first line of observational evidence that the rise in CO2 is absolutely the result of fossil fuels is that according to ice core records, it perfectly coincides with the Industrial Revolution. Many ice core studies exist from different locations, mainly in Antarctica. And you can see, for example, in the last 2,000 years of ice core data, CO2 was rock solid, 280 parts per million, and now it's rapidly rising. Again, I downloaded original data sets to make this plot. This is a mean of these different ice core data sets that stop at, I think, around 1900 with the modern instrumental data on top of that. These ice core records exist from multiple different studies, different organizations, different parts of the ice, all agreeing that for 2,000 years, CO2 was remarkably stable at around 280 parts per million, and now it is rapidly rising. If you want real papers besides the numbers I have here, the rise is not as dramatic looking because it is only showing the ice core data. It does not tack on the modern instrumental concentrations like I did on my graph. The second line of evidence involves simply counting emission sources. So taking different sectors at the national and international level, the Global Carbon Budget is a project that collects all of these CO2 emissions from agencies around the world, and they publish neat charts like this. By the way, this is the only chart that you need if you want to disprove the people that say that nature's emissions are much bigger than humanity's. They look at a number like 130 and compare it to 9.7 and celebrate how much bigger it is, every single time conveniently ignoring the 130 number coming out of the atmosphere. The numbers cancel out. It doesn't matter. 1 minus 1 is 0. 10 minus 10 is 0. 10,000 minus 10,000 is still 0. It does not matter what the magnitude in one direction is. The net is 0. And that's literally all you have to say for people who make that stupid argument, including, unfortunately, my government's recent Department of Energy report. The Global Carbon Project also publishes this kind of chart showing the fossil fuel emissions year over year at a global level. And this neat little map here showing main emission sources. The lines between the big cities are emissions from airline routes. And these calculations are done in 2 different ways. There is a bottom-up approach and a top-down approach. The top-down approach is known as the reference approach. It basically counts how much fuel enters a country and how much stock is left at the end. So it's production plus imports minus exports minus stock changes. It's a net accounting of the fuel itself. Like if you had 5 logs and you bring in 5 more and you burn some, now there's 3 left, you count that you burned 7 logs, basically. They combine that with a completely different methodology, which is a sectoral approach, meaning getting data from the organization in your country that measures electricity use, transportation, industry, add all of that up, and you should get basically the same number. And you can see for the last years here, these are those 2 different numbers. This is for the United States, and you can see that the 2 different methods agreed within about a percentage every single year. Here are 2019 numbers for the US and China, which of course are the two largest emitters in the world. And you do that for every country, add them all up, and you get a global number. India is number 3 and Russia is number 4, by the way. These emissions estimates can be confirmed independently by satellites, such as the CO2. You can see this study found direct measurements of 8 US power plants agreed to within 0.8% of their reported values. This, which used the Tropomi satellite and CO2 NOx emissions ratios to verify national estimates, again, finding that they agree. Upcoming satellite missions like the GOSAT GW was launched just a few months ago, and the Canadian GHG SAT project are both going to give us even better certainty into these national estimates. But for now, the fact that they agree with each other in these two different methodologies is pretty good assurance that they are generally correct. And indeed, if we assume they are correct and we take all fossil fuel emissions since 1850, we get around 481 gigatons carbon, which at 2.124 gigatons carbon per part per million can more than explain the rise in CO2 that we have seen. That is, the total known emissions of carbon can more than explain this rise to 427 parts per million that we find today. The reason it's less, the CO2 has not all stayed into the atmosphere. Some of it is being absorbed into the terrestrial biosphere.
Plants love CO2.
Thank you, Dr. Coonan. And also into the ocean. So we take the mass of the atmosphere in kilograms, convert that into moles. If CO2 increases by 1 part per million, then we just divide that atmospheric moles by 1 million. And we take the molar mass of carbon, which is 12 grams per mole, and use that to get us back in the units of mass. Here we go. And we see 1 part per million means 2.124 gigatons of carbon, 2.124 per each part per million. So as you get 1 more part per million, that means you have added 2.124 gigatons of carbon to the atmosphere. With our bottom-up estimates for 2023, we calculated 5.9 gigatons of C. 5.9 divided by 2.124, that gets us 2.78 parts per million. If we compare that, the actual measured growth rate in 2023 was 2.70 parts per million, which I would say is pretty damn close, and you can see more than explains the observed rise. I really like this last chart from Scripps. This is emissions versus concentrations, and believe it or not, there are 2 lines on this chart. It's just hard to tell because of how well they agree. And I think too that smoothness of it is important because that's absolutely what you would expect by a gradually on day-to-day time scale increasing emissions from industrial expansion. And that smoothness is not what you would expect if the rise were being caused by discrete large events such as volcanic eruptions. But pictures like this, they sure do look impressive, don't they? This is from the Pinatubo eruption in 1991, the largest single volcanic eruption in the last 100 years. And yeah, definitely putting a lot of stuff into the atmosphere there. I mean, it is worth noting, of course, that nothing that you see here is actually CO2. CO2 is invisible. This is mostly water droplets and ash that you're seeing, but whatever. Let's pretend it is CO2. We still have to contend with the fact that this famous photo was taken from Clark Air Base, U.S. Air Force Base, literally on the same island as Pinatubo. It's less than 25 kilometers away from the actual volcano itself. This is why it looks so spectacularly large. If you were to zoom out a little farther, that plume would look like this. Like smaller than the dimple on a basketball. Compared to this photo, by the way, that shows our energy usage. This is from the Globe at Night Citizen Science Project. If volcanoes are making this huge impact, where is it in the CO2 concentrations that we looked at, that we saw are being documented ridiculously well? Where are they? I mean, 1991 looks like any other year because volcanoes, spectacular though they are, only last a few hours, while this is every minute of every hour of every day for like 100 years. Now, volcanoes also have background emissions in between those famous eruption events, but still, if you take all of the volcanoes above ground and sum them up, you will get a value of around 51.3 teragrams of CO2 per year. Again, this is just the above ocean volcanoes. We can add to that the underwater volcanoes. And when we add every single source, every volcano, geological estimates, we get no more than 0.05 gigatons carbon per year. Fossil fuel emissions are 200 times greater than that. Put another way, if every volcano from every part on Earth were all added together, the emissions would be about as much as the state of Florida. So that's volcano combined with our bottom-up reporting of emissions of CO2 that actually do agree with the rise of CO2 in any particular year. That's all you need, right? Like, I like these bottom-up estimates because they are so transparent. Like, you could literally take any country, drill down, figure out what its associated contribution was from electricity, go and look at the number of kilowatt hours that they actually generated and distributed, take the exact kind of coal that they burned in that power plant. Like, there's no magic here. It's just counting. You can argue that these numbers are fake, but you'd better have some better estimates and an explanation for why your estimates are better. And, might want to think about it first, because I can guarantee you the same kind of people who might try to argue that these estimates are fake are the very same ones who will turn around and say something like, well, if you want to talk about carbon emissions, you should talk about China, right? And sure, we do need to talk about China. Do you know why we know we need to talk about China? Because of these numbers. Like, you can't just decide that these numbers are real when you want to make a point about China, but fake when you want to decide that they do not explain the rise in CO2 concentrations. They are the same numbers. And I mean, to me, this really sufficiently proves it, right? It's like if you never had a job and you suddenly get a job that pays you $1,000 a week and you spend $900 per week, and after 5 weeks, you see you have about $500. Maybe you have a reason to really not want to believe that the money came from your job for some reason, and you start investigating other sources of where that $500 came from. I think most people would probably consider that a pretty silly waste of time. If you had another significant source of money in your life, you would have much more than $500. The $500 balance is perfectly explained already. But with all that said, we still have 5 more lines of evidence to look at. And the next one is probably the most popular one. If you look at any other YouTube video that tries to address the source of the CO2 concentration increases, you're going to get this argument. And it is about the isotopes of carbon. There are 3 different kinds of carbon in nature: carbon 12, 13, and 14. The numbers representing the different numbers of neutrons, and all of these isotopes exist naturally in nature. Plants, it so happens, prefer carbon 12, and that the Rubisco enzyme binds with a CO2 molecule that has a carbon 12 atom at its center more easily than it will bind with a carbon 13 based CO2 molecule. Fossil fuels, like coal and oil, originally were plants. Coal is basically wood, oil is basically algae, and both of these used Rubisco to take CO2 out of the ancient atmospheres where they lived and store it now as solid carbon. And since carbon 13 is very stable, it never decays, we would expect this to stay the same even if the source of those plants is very old. And therefore, if the rise in CO2 is from a plant-based source like coal, we would expect the carbon 13 proportion of CO2 in the atmosphere to be declining because coal has relatively less carbon 13 in it compared to the background atmosphere. For example, in the ice cores, we can see stability for many centuries, and then right when we started to burn a lot of coal and oil as a society, the proportion of C13 in the atmosphere begins this trend of a sharp decline, which continues to this day. This change in the isotopic mix or relative concentrations in the atmosphere is also known as the Seuss effect. Different ice core study you can see here showing the same results. Here's another, and here's another. All of these ice core studies showing a basically constant C13 proportion throughout the pre-industrial era, and then suddenly and sharply declining exactly as the world started to industrialize and burn fossil fuels on a large scale. By the way, if you want to know why the pre-industrial values are shown as negative 6.5 rather than 0, it's because this is against a reference point, and we're in the world of geology right now, and they love their weird reference points, and they love old things. So they picked an old thing as the reference point for this carbon-13 ratio. And what is that reference point? The carbon-13 fraction that everyone has agreed to use is actually a single fossil of a giant squid. Looked like that, called the Vienna PD belemnite. It's from the late Cretaceous, somewhere between 66 and 72 million years ago. So yeah, it was like literally a little piece of fossil that they found in South Carolina and decided this was good enough as any to make as their reference. Now, the original BPDB specimen was ground up to analyze its isotopic ratios, so I can't show you a picture of it, but it probably looked a lot like this. This is a belemnite fossil. I like fossils, so I figured I'd pick one up for the video. And so the exact carbon-13 ratio that was found in that fossil is forever used as the baseline reference in every geology paper going forward, because why not? So if it's positive, it's greater than that reference fossil. If it's negative, it's a lower C13 to C12 ratio than that reference fossil. And the numbers are usually measured as per mil, which is like percent, but it's per thousand instead of per hundred. So small, but there are a lot of carbon dioxide molecules, so still very measurable variations. And you can see in the ice core records, the pre-industrial average was around negative 6.5 per mil. So slightly lower than what we got in the BPDB fossil. And in addition to ice cores, we have contemporary measurements using the same kind of air samples that we use to track overall CO2 concentration. We can also see this decline in C13 to C12 ratio. And there are also oceanic measurements showing the same decline because the atmosphere interacts with the ocean. And if it's going down in the atmosphere, it must also be going down at the ocean surface. And just by the way, saying that coal and oil should be lower in carbon-13, just because it's plants, it's not just an assumption, by the way. It's been measured. The C13 is much lower in coal and oil than we have in the atmosphere. You can see the numbers here, much less than the negative 6.5 mil that we have in the pre-industrial atmosphere. Keeling 2017 compared the observed decline in carbon-13 to that which would be expected purely by burning carbon-13 depleted fossil fuels, and found quite clearly that the combustion of fossil fuels is more than enough to explain the decline in the carbon-13 ratio. It overestimates it is actually because of the CO2 fertilization effect. A lot of the extra CO2 gets absorbed by plants, which prefer carbon-12. The plants of today prefer carbon-12 exactly as the ancient plants did. And when you add that effect, you see that it exactly matches observation. We can also see that the CO2 measured from volcanic emissions has a much higher carbon-13 content, typically than even the atmosphere. So if the rise in CO2 were coming from volcanoes, the carbon-13 fraction in the atmospheric concentrations should actually be rising rather than falling. And oceanic outgassing does not utilize Rubisco, so if the CO2 were coming from the ocean, we would not expect any Seuss effect. And in fact, the pH of the ocean would be rising rather than falling, which is what we see now, which we call ocean acidification. Similar to the carbon-13, carbon-12 Seuss effect, we also have changes in carbon-14. Now, unlike 12 and 13, carbon-14 is not stable. It decays with a half-life of about 5,000 years. It is created naturally in the atmosphere by high-altitude cosmic rays hitting the atmosphere. So, it's part of the natural carbon cycle. You are breathing in some carbon-14 based CO2 molecules right now. But fossil fuels are so old and have been locked away deep underground for so long that they basically have 0 carbon-14 atoms left. We are pumping in a source of essentially pure carbon-12 and carbon-13. We should expect the relative proportion of carbon-14 to also be decreasing, just as we see the carbon-13 to carbon-12 ratio. Not exactly at the same rate, but it's the same idea. Pumping in a biased source of carbon dioxide, a source of carbon dioxide that is isotopically different from that of the background atmospheric CO2 concentrations. And indeed, if we look at the chart, we see, whoa. So yeah, we have this huge spike right there in the 1950s and 60s. It's probably not for the reason that you're thinking though. I'm just kidding. It's exactly the reason that you're thinking. It's bombs, right? Bombs. The US, the Soviet Union, 1950s and 60s were testing huge hydrogen bombs right in the atmosphere. We're talking hundreds of times more powerful than Hiroshima. These fusion bombs created the perfect conditions to create ungodly amounts of carbon-14. It's not really a problem. It's not a health thing or anything like that. It's just complicates the signal. We're trying to see the trend in carbon-14 in the atmosphere. And right when we started to actually make measurements of the gases in the atmosphere is when we also decided to start blowing up giant hydrogen bombs in the atmosphere and completely messing up this carbon-14 signal. But in 1965, they finally agreed with each other to stop doing that, and atmospheric testing ceased and carbon-14 started to go down. Not because it was decaying, that still takes, a long enough time that you can't see it on a year-to-year scale like that. It was just settling out of the atmosphere and it was no longer being produced at these ridiculously high rates, so its concentration naturally started to go down. Except it's going down much faster than it should be. And this is because there are gigatons every year of completely C14 depleted carbon dioxide that we are adding to the atmosphere. So not only is the C14 that was left falling out of the atmosphere, there is 100% C14 free CO2 also coming into the atmosphere, which drives that proportion of C14 down a lot faster than it would be naturally. That rate of decline cannot be explained. It would be much less rapid, in other words, were it not for the large influxes of C14 free fossil fuels. But it is a shame that we can't go back farther than the 1950s. We don't have direct measurements from before the 1950s, and we can't actually use ice cores here. Because ice cores, the carbon is stored in gas molecules. The little bubbles are basically just trapped pockets of air. And the CO2 in the air bubbles, the cosmic rays can still get to it and hit the little bubbles of carbon dioxide trapped in the ice air bubbles and create new C14. So it contaminates the signals. But tree rings contain carbon that originally was sourced as CO2, but it is no longer stored as CO2. It is stored as solid carbon in wood. And the creation of carbon-14 by cosmic rays really only works on gaseous CO2, not solid carbon. And so we can get a signal from carbon in tree rings. We can't go back hundreds of thousands of years like we can with ice cores, but we can go back before the 1950s and see what the C14 levels were doing before we detonated a bunch of hydrogen bombs. And there was a famous study, Stuyver and Quay, 1981, showing that the C14 levels were indeed declining before 1950. And a lot of atmospheric scientists find this particularly strong evidence because any natural source of carbon would be part of the same carbon cycle in which the C14 is being made naturally. You can only get this kind of C14 depletion if you are putting into the air very, very old sources of carbon. So it's really a strong fingerprint for fossil fuel source for this increase in CO2. And the next piece of atmospheric evidence we're going to look at is oxygen. This is actually, I would say, my favorite of the lines of evidence because we all know that you cannot burn fuel without oxygen. Everyone knows that. Fire requires oxygen when it gets turned into CO2 with a release of energy. So if the rise in CO2 is due to something being burned, then oxygen levels should be decreasing by a very precise amount that we can calculate. And indeed, this decrease is not only calculable, it is observable. This was the first paper. You can see some other papers here that confirm it. The levels of oxygen in the atmosphere are going down. Actually, the best resource to look at this, if you head over to the Scripps O2 program, which is led by Dr. Keeling, who is actually the author of one of the very first papers to document this O2 decline effect. Dr. Keeling runs this entire O2 monitoring lab. Although in this case, we are not talking about Charles David Keeling from the Keeling curve. We are talking about his son, Ralph Keeling, who followed in his father's footsteps, also works at Scripps, and like his father, became the first to document a significant change in our atmosphere in the form of these reduced O2 concentrations. But it's not just that we see the O2 declining. Declining is easy. Is it declining by the right amount is what we need to ask. And so we can calculate how much should it be declining. By the way, we're taking the fossil fuel combustion rate here because we are looking at the moment of combustion. This is when the oxygen gets used. We don't care about the net CO2 emissions. We care about the actual amount of carbon that was burned. So we're taking the total fossil fuel emissions for 2023, 10.3 gigatons carbon, according to the global carbon budget. Actually, we'll use 10.1 in the calculations, which is the amount when excluding the cement carbonation sink. Now, we have to multiply this by 1.4. The reason for that is when you burn fossil fuels, it's not only carbon. There's also hydrogen present, and that also requires oxygen. So you're actually pulling in more oxygen than you actually need to create the CO2, because the full combustion requires additional oxygen for those hydrogens. And this is an average ratio of the actual mix of coal, oil, and natural gas that we have within the global energy mix. And then we multiply this by 32 grams per mole, just the molar weight of oxygen. And we get 37.7 gigatons of O2 lost, consumed every year. This is just, again, just pure chemical. This is what we're burning. These are the equations. This is how much oxygen we are consuming. And if we divide this by the total amount of oxygen in the atmosphere, which is 1.19 times 10 to the 6th, the declining rate, because this is 1 year we're talking about, the rate per year is 31.7 per meg. Per meg is the unit that's commonly used. It's basically percent is per 100, per mil is per 1,000, per meg is per million. So it's a very small change, of course, and the amount of oxygen in the atmosphere is huge. So take 32 per megs per year, and the observation amount, real decreasing rate that we see in these measurements at the Scripps Institute is 26 per meg per year. So the fossil fuel rise is more than enough to explain the decrease that we see in O2 concentrations. And it turns out it's more than enough because we actually do need one of those sinks that we threw out at the beginning, because the CO2 that is produced in that combustion is in fact being absorbed by plants through photosynthesis.
Plants love CO2.
Thank you again, Dr. Coonan. And in their love of CO2, they also make oxygen. So original calculation yielded a number that was between 5 to 6 megs too high. But if we take that 2.3 gigaton C land sink and multiply by the oxidative ratio for terrestrial photosynthesis, which is 1.05, we find a missing 6.4 gigatons O2 per year, which when converted back to per meg is 5.4 per meg per year, i.e. exactly what we were looking for. I've always found this O2 decline argument pretty striking and surprisingly the least well-known, I would say. It's a super well-documented effect and easy to understand. All you need to know is that burning requires oxygen. And by the way, we can also take ice cores and measure the historical oxygen levels. And if we take that rate from the ice cores over the past 100,000 years and compare it to, say, the measurement at Scripps of today, we can see that the rate today is a little bit faster than it was historically before the wide-scale combustion of fossil fuels. And by a little bit, I mean 2,600 times faster. I'll say that again, 2,600 times faster. Like even 50% faster would require a pretty damn good explanation. This is 2,600 times faster, and it exactly coincides with the point in Earth's history when fossil fuels are being burned on a massive scale. So if the rise in CO2 is not due to fossil fuel burning, please explain this dramatic increase in the rate of the decline in oxygen levels. Show me your secret, astonishingly coincidental alternative explanation from nature. I'd like to see both the evidence for its existence and a numerical calculation showing how it can fully explain this beyond dramatic increase in the rate of O2 decline. I'm not holding my breath. Pun intended. And we still have two more quick lines of evidence for good measure. The next is the hemispheric gradient. Basically, most of the world's emission sources are in the northern hemisphere. And even though air mixes quickly, it's not quite quick enough, and we get this gradient effect. We consistently measure that northern hemisphere CO2 concentrations are greater than southern hemisphere, and this effect can be seen in the carbon-13 to carbon-12 ratios as well. So again, any alternative explanation for the CO2 has to be consistent with this clear hemispheric gradient. And finally, more recently, we have economic correlation. So normally trends and spikes in the economy are too subtle to notice an actual CO2 parts per million change. But 5 years ago, we did have such an event, and we did have satellites in the sky ready to track it. During the COVID-19 pandemic, many countries saw an unprecedented fall in transportation emissions that we had plenty of satellites up in the sky ready to check. This study in Japan, you can see 2020 in red here, Zhang 2020 here, and Turner 2020 here. If CO2 were rising from some natural source rather than fossil fuel emissions, why would it be sensitive at all to our economic activity? And the answer, of course, is that the rise in CO2 that we are seeing is absolutely due to the wide-scale combustion of fossil fuels. So if you see someone trying to claim that the rise in CO2 is not real or natural, challenge them. Show them these lines of evidence. Ask what is their alternative hypothesis that they think better explains all 8 lines of this evidence. And when they can't do it, ask them why they are so sure then that they are right. Because there is this growing tendency to take pride in rejecting mainstream education in favor of sensational and, frankly, pretty darn alarmist conspiracy theories. Practically everything they say is more horrifying than anything that I've seen in the so-called alarmist IPCC reports. They repeat lies like that humans are not responsible for the rise in CO2 simply because they were told to repeat these lies. And then the hilarious dark irony when they turn around and call themselves skeptics. If you believe the rise in CO2 is natural, you are the one believing the propaganda. And it's not necessary. Like, the chart is not that scary. At least not to the point you should feel the need to do all these mental gymnastics to explain it away as some powerful and perfectly orchestrated conspiracy. That conspiracy does not exist. And I promise, reality is less scary than whatever the hell is going on in the brain of someone that thinks that it does. So yeah, thank you guys as always. I hope this will be useful, and we'll see where the channel goes from here. But so far, still enjoying making the videos, at least when I have time. It's hard lately, but I was happy I was able to get this one out for you guys. And yeah, thanks for watching.